Hi, my name is Alena and welcome to the project demonstration for my implementation of the maximum subarray problem. Just to give a quick overview of what the maximum subarray problem is, essentially given an array A, the algorithm will search for a contiguous subarray that has the largest sum. So given an input of numeric positive and or negative values within an array, the algorithm will output a tuple. The tuple consists of the starting index of the subarray, the final index of the subarray, and the maximum sum of the subarray. Moving on to the implementation, I used Google Colab as my primary development environment for writing all of the code and testing it, and I used Python as my programming language. And the three libraries that I used from Python include math, time, and NumPy. Here we see the algorithm definitions. So the first algorithm in this list is the brute force algorithm, which implements two loops. The outer loop provides a starting index I, such that the inner loop can test all possible subarrays that start at that index. And if any of the tested subarrays are larger than the current maximum subarray found so far, we update the maximum subarray and continue the search, and it repeats for all possible contiguous subarrays. So the running time for this algorithm is n squared, as it requires a nested for loop. Next is the divide and conquer approach, and this is a more efficient algorithm which recursively divides the array into halves so that we can search for the maximum sum within the left half, the right half, and the midpoint crossover. So the midpoint crossover, finding the maximum here, is done in this function, and this is executed in linear time. And here, this bottom function is used for the recursive calls and dividing the array. And in total, this running time for the algorithm is n log n. Next is the Cadane algorithm, and this algorithm is the most efficient of the three, and it essentially makes use of a dynamic programming approach. And it considers the following concept where the local maximum at a given index I is the maximum of A of I, or the sum of A of I and the local maximum at the previous index, so that you can see are these two if statements here. And the running time for this algorithm is linear, it's O of n, and it requires one traversal of the entire array. Moving on to an example, here I have a simple array A consisting of positive and negative integers, and I'm going to run each of the algorithms on this array, and as you can see the results are the same across all three methodologies. The starting index is shown here for the subarray, and the final index is shown here, and the maximum sum, 7, is the result for this particular array. So you can see the subarray starts at index 2 and ends at index 6, and the sum of these elements is 7. Moving on to the code that will run all of our test cases. Here we have the input size array, which specifies the desired input sizes for testing. Here I've only specified 5 different sizes, but in my actual program I have used the ones that match my report, which I'll show later. And after we specify the input sizes, the program will write to 2 CSV files. It will just write the headers for each of the columns. And there are 2 CSV files. The first one is empirical.csv, which records the execution results of each of the algorithms across all of the runs and all of the input sizes. And the second file here, empirical_average, records just the average running times across the m number of runs for each of the algorithms. And I used 2 of these CSV files just to ensure that I can cross-check my results and make sure that my code was running as intended. As you can see, next we loop through all of the input sizes, and for each input size n, we create 3 empty lists or arrays. These are used to store the running times for each of the algorithms across the 10 runs. So we have the brute force, divide and conquer, and the Cadane algorithm. And so for each input size n, after we create those arrays, we run for 10 runs, and for each of these runs we create a random array consisting of integers between -100 and +100 of input size n. And once we generate the array, we go ahead and run all 3 algorithms, And for each algorithm, we log the start time as a variable, the result of the array, and finally the final ending time for the specific algorithm call. So this is simply just the difference between the current time and the recorded start time for that algorithm. And once we calculate the running time, we append that to the array that we saw earlier here. And we do the same thing for all three algorithms, and they all run on the same input array A. And once all of these executions are finished, we run this code, which will save the results for this specific execution in the empirical.csv file that I mentioned earlier. So we record the input size, which run number it is, the brute force time, the divide and conquer time, and the Cadane algorithm time. And finally, as a sanity check, I checked to make sure that all three algorithms are producing the same results. So this will essentially print a Boolean value that tests to see if the maximum sum for the subarray is the same across all three algorithms. And so once we run through all m values in this loop, we go ahead and record the average values by using np.mean, and this will record the average over the 10 runs in this loop. And once this completes, it will have the results stored in both of these files shown here. So we can go ahead and run the code here, and once we run, we see all the print statements. These print statements are just printing what gets logged in the empirical.csv file. And now we can go ahead and take a look at the results. So empirical.csv shows each execution, the running time for the brute force, divide and conquer, Cadane, and whether the outputs match. And so it shows the size n, and the run number is here. And as you can see, there's 5 pages, so it calculated all of the results across the 5 specified input sizes, like so. And the empirical average CSV file is just the average running times across the input sizes for each of the 3 algorithms. Even though I used Google Colab as my primary development environment for writing the code and testing it, in order to generate the data across all of the experiments, I used FAU's HPC services, or high-powered computing, which essentially let me use FAU's high-performance resources in order to run my jobs. So here you can see I have the maximum subarray code as a Python file, and I will just show it briefly. So here's the same code that I just went over earlier, but instead of a notebook, it is a Python file. And as you can see, I changed the input sizes to match the input sizes specified in my report. And in order to submit the script as a job, to essentially let it run in the background on FAU's resources, I needed to use a shell script in order to submit the job. And from here you can see I used the long queue because the job takes more than 6 hours, and I specifically requested a node that used an AMD CPU in order to have the code run a little bit faster. And here you can see the same CSV files were generated from before, and these are the CSV files that I used for generating all the tables and the graphs that you see in the report. So here's the average and the empirical.csv files like you saw earlier. Lastly, I just wanted to show how I generated the tables and the graphs that you see in the report. So I used Google Sheets. Essentially, I created these tables which have embedded formulas to calculate the ratio and the predicted running time, and also the value for C1, which is the maximum of the ratios, and the ratios are calculated using the empirical running time divided by the theoretical complexity. And I did this for each of the algorithms. And then this page on the Google Sheet is used for generating the graphs. So this is saved as a CSV file and imported to another Google Colab, which uses the Plotly library. And essentially, I just created the graphs using this framework, and it uses that CSV file that I just showed from the Google Sheets. Okay, that's it. Thank you so much for watching.